Hello, everybody. We are going to be learning about everybody's favorite, the neuron, today. Um, sure, we're all set. Okay, I will say that I forgot how much I detest making videos to put online because I wasted just about an hour because of some bad button pressing. So, um, if you think listening to the Neuron lecture is bad, imagine having to give the Neuron lecture several times in a row. And that will tell you how my day is going. So in the best of shape to talk about the Neuron today. So before we start, I want to talk about a couple things. And this is really just parts or piece of advice for you. There are basically two groups who are probably going to be here today. One group is the intro psychology student. And if you're here because you have exam coming up, most likely, and you want sort of a walkthrough of the neuron itself. Commendable, absolutely commendable that you're doing that. I do have some advice for you, though, which we'll get to in just a second after I acknowledge the other group. The other group, of course, are probably the seniors who are preparing for the ACAT or upper class majors who are learning about the next parts of the neuron in other classes. What I will say to you is that you should have listened to the advice that I'm giving to the intro students. So this really is for everybody. And here's the advice I have for you. The advice is that what we're going to be doing today is learning the basics of how the neuron works, the components, how it fires, how it communicates, etc., all the way through. If you're planning on becoming a psych major, you need to understand that everything we're doing in intro psychology is really setting out the baseline of what we're going to cover. It's sort of once through every topic or the important components of every topic that you're going to run across throughout the rest of our curriculum. What that means is what you learn in intro psych is supposed to be retained as you go forward, because we will be adding on in several other classes information about the neuron and about classical conditioning and about correlations and about whatever topic you're covering in intro. There's another class, at least, in which you're going to run across some of that information before. Our assumption is and always will be that you have learned what was necessary to know in intro. We understand that that is the basis that everyone is starting from, and we are going to build from there. So what that means is we're not going to recover this every single time we come and talk about the neuron, for example. So I talk about really where we're leaving off today with this neuron lecture, the synapse, the end of the neuron. I pick up on that in abnormal when I talk about drug interactions and how it affects how different neurons communicate to each other. I am assuming, and I will be honest, I test on knowledge of the entire neuron that I know that you had. You cannot not know anything and then just jump in at the very end of something. You have to retain all of this information. And that's going to be true of every class. One of the things that really separates the students who find that they are succeeding in psychology versus those who don't is that those who are succeeding understand that you don't just toss out knowledge after an exam or after a semester. You need to have this knowledge, learn it well enough the first time, and you're going to build upon it over your 4 years. Otherwise, you're going to have to relearn it every time. And if you're forced to relearn it, you're going to be behind the rest of the class. So please, just as someone who has seen the body count that sometimes comes with intro psychology, um, just having the general understanding of something is not going to be enough. We really do like to focus on the details in our discipline, and all the stuff we're talking about in this PowerPoint are things that I would expect every student in class, in abnormal class, to know before they set foot. And I'm going to expect that all of that information is there when I begin my discussion of the neuron at that point. So as I extend the knowledge, I believe that everyone is up to date on what the neuron is. So if you discard that information, you're going to be behind, and that's going to cause a lot of issues as we build more and more across various classes. So please learn this, learn it well enough, and retain it. Um, certainly for the test, if nothing else. But so we don't have to, you don't have to, I don't have to keep relearning it. You have to keep relearning it over your 4 years if you're going to be a major. This is stuff you need to hold on to. It's important all the way through. Okay, so there's that general advice. The second thing I want to mention, because intro psychology sometimes gets upper-class women who take partner classes and maybe taking their sophomore, junior, or senior year, and they're going to be coming from all sorts of different majors. Obviously, you're not going to be a senior psych major taking intro. That just cannot happen. So you might have taken, let's say, a couple biology classes along the way. If you have taken extra classes and have learned about the neuron in other courses, what you are going to discover today is that I am taking a couple of shortcuts. There are some things that I am going to oversimplify. There are some things that I am going to skip past as if they're not even happening. That is because we are an introductory psychology course, and we want to focus on the things that we need to build on in our other courses. This isn't a biology course, so we're not going to spend an exorbitant amount of time on something that is really just the biology component. We're setting things up for other psych classes. So we will be skipping over some things. We will sort of be oversimplifying some things. That's appropriate because this is the first time the psych students are probably getting introduced to this, and we know where we're going to pick up the next part of our discussion on any of these topics. So yes, you may have an overwhelming desire to say, hey, you skipped something. You are absolutely correct. Congratulations, you have pointed out that I have done that. In a biology class, there's something that we're going to do a little bit with, but not much. Something called a voltage gate is going to show up in today's presentation. A biologist could spend a week or more talking just about the voltage gates. We are not, because we don't need to worry about voltage gates beyond one simple fact. We need to worry about different parts of the neuron that biologists may not be all that concerned about themselves. So understanding where you're at, understanding that this is introductory. And as it is introductory, let me just also warn you that there will be far more details in here than you want. And do you need to know them? Yes. Which ones? All of them. Okay, psychology is very detail oriented. I have weeded out everything I can that isn't absolutely necessary for you to know. And what that means is on exam days and in other classes, this is the bare minimum, but everything today is going to be expected that you will have maintained. What that means, again, as I said before, is just having a general sense of things is not going to be enough. So neuron questions can happen in multiple choice, in which case you might get lucky by just recognizing something, but they may also show up in definitions. They may also show up in short answers. They may also show up in essays, even at the introductory level. And what that means is that you're going to have to be able to generate all the terms, all the facts, everything that is necessary for this process to be understood. Remember, we only can grade what you put on the page. We are not going to fill in the details for you. So you need to understand all of the components well enough that you can recreate them. Again, that is just sort of fair warning for you. You can't count on just getting lucky and recognizing something. If I gave an essay question, and truthfully, I could say instead of exam one with all sorts of questions, I could just give one question, one essay question, tell me everything about the neuron. And you would need to sort of put down every fact that I'm going to say to you. We won't do that, by the way. But that is something that's how the situation would change very quickly. So just having a general sense of things, not necessarily knowing the names, not necessarily knowing all the facts and figures, that will come back at you on testing. So again, that's I'm trying to warn you, take that for what it is worth. Okay, that being said, let's turn to happier things. And of course, by happy, I mean the neuron, because who doesn't love the neuron? Other than every intro-psych student who's ever come across this particular lecture. Okay, so some basic stuff to get us started. There's only one sort of factual thing, and that's really our definition here up front. The neuron is just a specialized kind of nerve cell, but these are the nerve cells which comprise the brain, the spinal cord, and the nervous systems. Again, all of the nervous systems that are there. Obviously, the brain is where we're going to spend most of our time. But in sensation perception, the spinal cord and the nervous systems are going to be important. In other classes, the nervous system sort of shows up, but the brain is really where most of our time is going to be spent. The next lecture after the neuron is the brain. Okay, we're not going to have another lecture on the nervous systems at this point, but there may be sort of a short description of them in another class. But the brain is going to be our focus, so that's really where our lecture is going to be sort of focused around. Most of the neurons that we have in our body are generated before birth. And obviously not before conception, before birth, so in the in utero period. And there is some new evidence in the last decade or so that neurogenesis, the creation of brand new neurons in the body, actually is occurring in some regions of the brain and body across life. We used to assume that all or almost all of these occurred before birth, and we just kind of grew into them. It's a weird way of thinking about it, but that's kind of what people thought. Although that was a while ago, but they thought that. But we do now understand that some neurogenesis, although again, a very small amount in total, is going to happen throughout other parts of the lifespan. Our neurons, as they're developing, again, at their peak, are going to be developing at a rate of about 250,000 per minute. And there are many minutes in a day. So when we're at our peak, we're going to be creating a whole bunch of neurons. Again, these are microscopic. We're not going through, or some of these are microscopic, but we're not going to be able to go through and count. Okay, so we're going to have to do some estimating here. The peak is about 250,000 per minute. I'm not going to ask a question on that because that's not something we know for sure, but that's the rate at about we think these things are happening. Not all the neurons that we create are going to survive, even from the beginning, but certainly throughout the course of life, we're going to be losing neurons left and right. We're going to be losing parts of neurons left and right. If you are drinking caffeine, if it's junior banquet week, a whole bunch of neurons are going to get lost, or parts of neurons are going to get lost. If you're an athlete and there is contact on the field, you've probably lost a couple of neurons along the way. Although it's a Sweetbriar, we're not quite in concussion season because right now I'm on spring break, but as the athletes sort of gear up again, we see a lot of kids who will get concussions or fall off the horse. And if they hit their head, we're going to see neural loss at that. That's why it's important to wear protective gear. We can manage to lose this. And during normal development, we are going to produce extra neurons because we're planning on getting rid of some of them. It's going to work basically like this. Again, this isn't on the PowerPoint slide. You don't necessarily need to know it, but just to sort of fill in the background to give some context for all of this, there's a concept that we'll roughly adopt, which is something called neurodarwinism. Neurodarwinism says that over time, we're going to create pathways in our brain. Neural pathways are a series or a chain of neurons that fire in sequence, and it is like a road, a well-used road, if it becomes a strong pathway, that a lot of information is going to travel down. There are also be neurons that are relatively unused. Okay, we have a whole bunch of them. Some of them develop and get used and turned into a pathway. Other ones just sort of exist on their own out there. Excuse me. What will happen is that during just part of normal development, we are going to create extra neurons, and then we're going to cull them. And cull means to destroy, to kill. So there are cycles of proliferation. Proliferation means to create, and then culling, which means to restrict, limit, or kill across development. This is going to happen early in development, but will happen several other times. Now, neurons themselves, with a couple rare exceptions, do not regenerate or repair once they have been destroyed or damaged. So once one is broken, once one is destroyed, once one is non-functioning, that neuron is essentially dead. Okay, we hope it's going to get flushed out. It may not. When we talk about something like Alzheimer's, Alzheimer's is really an accumulation of dead cellular material. It could be from neurons. It is a very big component of this. They're sort of clumping together in some way. So once we lose a neuron, it is lost to us. Okay, we'll talk about it not all hope is lost. So don't worry if you're an athlete or you don't ride a horse well and you keep falling off. We'll deal with that a little bit later. Notice I didn't accuse you all of drinking, okay? But it was implied. Okay. Now, the overall number of neurons is important. Okay, great. It's something I can throw out there. Again, it's an estimate, but I can throw it out there. That's not really the most important thing in terms of how the brain is going to function. Most of the functional improvement that is going to occur is going to become become known as synaptic expansion. The synapse is the area at the end of the neuron. It is how one neuron communicates to the next neuron. That expansion, that growth, that change at that part of the neuron is really going to be what's most important across life for us. At this moment in your life, most of you should be college-age students, so probably under the age of 25. And what we're seeing at this point in your development, your brain is still developing. Not all of the brain, but certainly the frontal lobe and the prefrontal cortex is going through a lot of change right now. The change that is occurring is not you're getting a whole bunch of new neurons. You're seeing a lot of growth in the synapses, the connections between neurons. At around the age of 25 or 26, that growth is going to stop. And then after that, that's pretty much it. Okay, unless some of that neurogenesis hits in the right place for you later in life. So my brain, it's cooked. This is as much as it's going to do. Damage now is going to just accumulate. For the rest of you, until the age of 25 or 26, there is still chance for growth. That is why you want to learn things now, because it's much more difficult after your pathways have not been created. So please take use of your time in college, explore culture, explore different languages, learn different fields, read a whole bunch. The idea is your brain is right now ready for that information. If you don't do it now, it's going to be harder to learn it as easily if you try to do it later. Okay, so that's my old man advice rather than psychologist advice. Okay, so the synapses and the growing connections between neurons is really what's going to carry most of our development. The neurons themselves, most of them, again, are going to be created before birth. But again, we're going to have excess that we can certainly get rid of a large number of them with no notable deficit in function. Some of it is just going unused. Excuse me. All right, so other building blocks. Estimate 86 billion neurons. Now, again, would I ask that question in an exam? No, because that's a guess. That's an estimate. And we can estimate even further from that 86 billion because there are multiple connections from a neuron at the synaptic level. We're going to see that there are potentially trillions of synaptic connections. So that's just to give us a ballpark so you understand the field in which we're talking about. So when I say that if you're drinking caffeine or you have a head injury, you've killed some neurons, yeah, you've got a few extra. There's some of that 86 billion that can pick up the slack at this point. So again, that doesn't mean let's go out without a helmet. It does mean let's not panic about things that are really not things we should be panicked about. Panic about your exams coming up, panic about the end of a semester. Those are things that are really much more urgent than have I run out of 84 billion of my neurons. Okay, so neurons, though, are like other cells in the body, and some of these things are going to become very important. So this would be where we would want you to start paying attention again. Neurons are like other cells because they have a few qualities. The first quality, and this one actually is very important. The first quality that neurons have, like other cells, is going to be that they have a permeable membrane. Permeable just means that it's going to open up and close and allow some substances in and out of the cellular membrane. So at different points in development, different points in our firing process, a neuron will open up. Ions that are in the outside environment may flow in, and then eventually they may be pushed back out. All right. So the idea here is it's going to be this movement of chemicals in the brain as we open and close these membranes that the neuron firing is going to happen. So yeah, that is an important part about the neuron. Even though other cells have that exact same quality, that still is an important part of our discussion for today. Something not as important, but still a fact. The cell body also contains the DNA code for the organism, which means our DNA helix, the blueprint of us, is contained in the cells, in the nucleus of the cells. Now, for us as psychologists and learning about the neuron today, I don't care about DNA. I care about a lot in other classes. I don't care about it today. Now, I actually just say that in case there are biologists listening, because it's always fun to think that they're gasping that someone would say something like that, something so foolish. It's not important. DNA is destiny. That's just to mess with biology students who really should have taken interest psych their first year like regular people. Just saying, just starting some trouble with the second floor. But we're not going to make any use of that today. Other classes will, but for us, DNA is not going to be something we're going to be dealing with further. All right, the third one, I will start the sentence and then let you finish it. Mitochondria is, and if you've been a student in the US educational system, without even wanting to, you thought or screamed out, the powerhouse of the cell. Okay, now, if I ask further, what does that mean? All right, it gets quiet again. No one really knows what to say other than that particular statement. Don't feel bad if that is you. I'm going to oversimplify it here, so I'm going to meet you in the middle. Mitochondria, along with other things, there are other things that are in the cell as well, but mitochondria is the one that you are most likely to be familiar with. I don't want to be introducing new concepts that don't go anywhere in this particular lecture or later on in our semester. So mitochondria, you're used to it. Let me build from that. Mitochondria and some other things conduct the protein synthesis. So it's going to synthesize proteins and create the ions. We'll talk about those later. And the energy necessary for production of energy within the cell. So when that neural impulse starts moving, energy is going to be created because ions are moving in and out of a cellular membrane. And the polarity of the neuron is changing, and that's creating energy. So, but mitochondria is part of that. We're not going to deal with that component of it. That's, again, for the biology courses. We deal with like the aftermath of that. All right. Now, neurons are unlike other cells, and this is what makes a neuron a neuron. This is why we classify them as something other than a simple nerve cell. And it is here, the fact is that they can communicate, and it's that communication ability which makes them different. Now, of course, notice that communication is in quotes. So that means it's really like a computer sending along information. This is binary code, ones and zeros at the chemical level. Messages are being sent. So again, communication in its broadest sense is what we're dealing with here. But other cells that aren't neurons do not do this. Okay, so neurons allow for communications between one neuron and another. All right, you will often hear that when we talk about neurons, that the signal itself is something that we refer to as electrochemical. So it's electrical and it's chemical, the whole thing together, electrochemical. That refers to different parts of the process. So within the neuron, while it is within the neuron and again moving, that is electrical activity, or essentially electrical activity. It's slightly different, but we'll again overlook that because we don't necessarily need to get into that level of specificity on this topic. So within the neuron, the movement, the power, the energy is sort of like a neural impulse that is acting according to electrical changes, polarity changes between the inside and outside of the neuron, for example. As we communicate between cells, going from one neuron to the next, which happens at the end, which is at the synaptic level, this is not done by sending an electrical-based signal. This is done through a chemical messenger. And the chemical messengers we are talking about are called neurotransmitters. And we'll talk about the basic ones as we get near the end of the PowerPoint. But communication within a neuron, essentially electrical. Communication between neurons is essentially chemical. All right. Now, here is our typical neuron. Neurons come in different sizes and shapes. They have some qualities that some neurons have qualities that other ones don't. There are, again, size differences. What they look like physically may differ. Here we're going to be talking about the typical neuron, the things that are true of almost all neurons, and really with one exception. This is true of really every neuron that we're going to be running across. The difference is going to be I'm sorry, I'm having some trouble with the English language for just a second. Part of that, this is why I hate doing this on video. The one part that's going to be different, if you look at this neuron, are these little bubbles right here, these yellow bubbly things. That's going to have to be dealt with separately. That is sort of like some neurons have them, others don't. It's important if it does or it doesn't. But the fact of the matter is, this is the one component of everything we're going to be talking about, which is most likely to vary from neuron to neuron. Everything else, it's going to be there. Okay, so this is our typical neuron. But if you look at the textbooks, you'll see that they can look slightly different from each other in terms of how bunched up they are, or how spread apart they are, but the components are all going to be the same in terms of the ones that we're dealing with. Okay, so here's a neuron. This is a picture we're going to be using as we go throughout today's PowerPoint. Okay, so let's start with all of these branches. I am hoping that you can see my cursor on your screen. If not, I'm referring to all these branching extensions off to the left side of this particular neuron, or the top of the neuron. So all of these things right here are called the dendrites. Notice I have tried to say that every single place where there's a yellow line, that refers to a specific dendrite. So again, there's a lot of them here. Each and every branch, each and every sub-branch of this is a different dendrite. So we have a whole bunch of ways that we're going to find out we can get into this particular neuron, because that's what the dendrite does. It's going to be a place where a neural impulse, a neural signal, actually at this point we'll call it a signal. Later on, I'll start calling it an impulse. At this point, a neural signal is going to be received. This is the entry point into the neuron, is at the dendrite, and it's going to take that neural signal, and it's going to transport it further down into the neuron. Okay, so the dendrites themselves, branching fibers, again, all branching off this sort of big glob here. This we'll eventually call the soma, but all of these branching extensions are different pathways into the neuron itself. Okay, so the dendrite receives signals from other neurons or from a sensory organ, if it's a sensory neuron, for example, and carries them from the dendrite down its dendrite to the soma, or the cell body. So it's just going to take a signal received here and transport it down to the soma. So this is our entry point to the neuron. So at this point in our discussion of the neural impulse and the firing process, a signal has been received. So let me add a signal to this. Now, I hope this works, but hold on. There we go. Notice that what is happening is appearing at the end of the dendrite and is just moving down into the soma, and that's going all the way to the back of the soma. We'll talk about that in just a second. But no matter what branch it enters from, it's going to go down toward the soma and then towards that one part of the soma where our signal is ending up. So let's talk about the soma for just a second. For us, not the most important component. We're not going to do much with this, but it is part of the story. Okay, so let's deal with it as we need to deal with it. Soma in general, because this will show up throughout psychology, soma just means body. So this is the body of the neuron itself. So we have something called somatoform disorders in psychology. Those are body disorders. Okay, so soma just means body. The soma contains a nucleus, contains the DNA, which again, I don't care about biologists today, but also those chemical processing structures. So all the powerhouse activity is going to be happening in here. The structures that are in the soma are going to transform glucose, so sugar, and oxygen that is coming from the bloodstream into the high energy molecule known as ATP. We don't need to worry about that, but ATP you may have run across before. So if so, I just want to connect this to knowledge that you might have. But notice that all the dendrite did, it was just a pathway. The signal was received there, so it entered the neuron at that point, took that signal, passes it down to the soma, and then it goes to the back part of the soma. Okay, so the signal moves to the soma and then to the back. And that back portion, the next part we're going to be talking about, is something known as the axon hillock. Oh, I'm sorry. Because he is ever present in my existence. This is Otto, in case you have not heard about him before. He is my co-pilot in all things. He keeps me on the straight and narrow. He is a whopping 12 pounds and thinks that he runs the household. He doesn't. He likes to think he does, but he doesn't. Okay, but thankfully, Otto is on his best behavior. He is going to remind me, and I put this in to remind me that before I go further, I'm going to take a little bit of a detour, very brief, but it's important, and he's there. Also here, of course, is Mr. Carrot. And again, just to share a little bit about myself, Otto is my co-pilot, you could say in life. He's my buddy. I do not happen to be Otto's co-pilot. Mr. Carrot is actually Otto's co-pilot. So if it was a burning fire and Otto could choose to save me or Mr. Carrot, I want you all to understand that you need to call campus security because Otto is not going to be saving me. He is be saving that damn carrot. So he loves the carrot far more than he does me. Now, also to let you know, because you're probably thinking, oh, he's so adorable. Okay, he is. He's very photogenic for a dog. Mr. Carrot, his best friend, that is not necessarily the current Mr. Carrot. That is Mr. Carrot number 8. Because when Otto gets bored, he sometimes just eviscerates Mr. Carrot. And there's stuffing of Mr. Carrot and a random squeaker of Mr. Carrot found all across the household. He always nibbles off the fronds first and leaves them there as evidence of his crime, and then he just devours the rest of Mr. Carrot. So again, I may not be his co-pilot. That may actually be a good thing. But again, I'm not his favorite person. I'm just the thing that gets him food in the household. So don't fall for those big eyes. Just saying. Okay, what he wants to remind me is that there are 2 different kinds of signals that can be sent and received, obviously. So 2 kinds of signals are being they arrive at the dendrite, and these signals are being passed down through the soma down to the axon hillock, which again we'll pick up with in just a couple seconds. 2 kinds of signals can be sent, either an excitatory signal or an inhibitory signal. An excitatory signal means to excite, to create. In our purpose, it means to continue, to keep it going, to keep the action going. An inhibitory signal means to inhibit, to stop. Okay, so that's going to be a signal which is going to say stop what we're doing. Okay, so let's deal with the excitatory signal first. Excitatory signal is created, a neural impulse is created. And again, we'll eventually be calling this that it's technically being sent. When we reach the action potential, we'll get there. It's generated before that, but it's sort of starting the process when we reach our first action potential. It's going to be sent down the axon down to the next neuron. So all the parts we're going to be getting to in a bit. An excitatory signal, again, means to continue. So if we send this signal, what the signal is sending is saying fire, continue firing, continue sending. Keep sending because we haven't finished our task yet. If the task is to activate a gland, okay, to release more dopamine into the system, the entire chain of neurons, and maybe thousands or even millions of neurons that get activated in a sequence, probably not millions for something like dopamine, but we're going to see that the signal has to be sent until it reaches a place where the person with the key, so to speak, to release the dopamine can receive it. So an excitatory signal says, keep sending until our stated goal of more dopamine is going to be achieved. Okay, so excitatory says, keep sending, keep sending. We haven't finished the task yet. Inhibitory says, stop. Okay, so a signal is being sent that says stop. When the dopamine has been released, another neuron, which is sending a signal, says, up, it's been released. Stop the message. Stop releasing it. We've done what we need to do. So again, a signal is sent to just continue what we're doing, whatever that task ends up being, or to stop because we've achieved whatever that end state is. So an inhibitory signal prevents the generation of an action potential that's going to carry the signal forward. It's going to say stop firing, and it's going to stop a signal from being sent to the next receiving neuron. Okay, at some point, a stop signal doesn't just keep getting sent, it has to stop. And what it will do is at the end of the process here, it's probably going to end up blocking a pathway so that a signal can't continue further. Okay, a little bit beyond our capacity for today, but those are the two types of signals we are going to have. So thank you, Otto and Mr. Carrot, for reminding me of that. All right, now looking at this, you can see that I have a whole bunch of signals being sent. And again, it's sort of on repeat. So if you're sort of catching in the middle, it's a little bit confusing. But each of these signals that are being sent, the red ones are excitatory, the blue ones are inhibitory. They are being picked up at their dendritic location. They are all traveling down their pathway. Some is going to be longer than others, down to the soma. And then all of them are going to the back of the soma, which is where the axon hillock is. And that's the point where the yellow lines are intersecting. If you can see my cursor, this right here is the axon hillock area. It's a junction between the soma or the cell body and the axon, which is this long branch going down here. So the axon hillock is located between the cell body and the axon. And the idea here is that it's at this point, we're going to sum up the incoming voltage, okay, the inhibitory signal strength versus the excitatory strength, and determine if we are going to generate the action potential, which is, again, the start of that firing process. If so, if the stimulation is strong enough and it is recognized, then a signal is going to be generated and sent down the axon itself. Now notice, though, that in this example, we have both excitatory signals and inhibitory signals. Okay, so let's go a little bit further, and then we're going to end up going back. So let's sort of focus in for just a second. Basically, let's just do a close-up of this area. So there's where we're at the end of the animation. That area right there is the axon hillock. So what is there waiting for us and all of those signals at this moment? Okay, so here are the signals. And notice that we have the red ones, which in our case are going to be excitatory. The blue ones are going to be inhibitory. This thing right here, which is a new shape in our diagram, is something known as a voltage gate. Again, we're going to do very little with this. It's a much more complex process than I'm going to be talking about, but we just need it for a simple function to go forward. So at this point, those excitatory signals and inhibitory signals are clustering up at the axon hillock, and it's going to have to pass this voltage gate for that signal to be sent on. Okay, before it can go down the axon, it has to pass through this voltage gate. Okay, so what is a voltage gate? Well, a voltage gate is really just a check. Is a signal strong enough for us to recognize? Is it a signal that is strong enough to send? Okay, so what we're going to be talking about is the strength of the signal. And the idea is that if the strength of the signal, whether it's an inhibitory signal or an excitatory signal, if the signal is strong enough, and we're going to say, we'll find out there's a threshold. If it's stronger than that threshold, we exceed the threshold, the voltage gate is going to open. It's going to allow the signal to go through, and the action potential, the first one, is going to be created to carry it down the axon. Okay. We'll get into all of this, but this is just our holding point for just a moment. Now, each of these cells is easiest to think of them as having a positive and a negative charge. The excitatory ones are +1. The inhibitory ones are -1s. So these things are going to cancel each other out. So to have a strong enough signal, you have to have a predominance of one kind versus the other, if nothing else, or enough of any one kind, if there are no other kinds of signals being sent. Strong enough to go beyond that particular threshold. If it is strong enough, the gate opens, process is going to continue. If not, everything is just going to stay clustered up here. Remember that this is biology. So these signals are not going to last forever. They last for an amazingly brief amount of time. At some point, the signal decays it vanishes, it disappears. So it's not like we're going to just keep building up and building up until we finally reach threshold. Some of these are going to vanish. Some of these are going to disappear. Enough of them have to cluster at a moment where a signal is strong enough to sort of surpass this threshold, which essentially means we recognize it. It's a strong enough impulse, a strong enough stimulation that it is something that passes into our conscious awareness. Okay, but the voltage gate is the gate we have to get through. It's the gatekeeper in some ways. So as we're here, now this detail comes into play a little bit later, but it makes sense to introduce it here. So that's what I'm going to do. So I'm jumping ahead of the skis a little bit, but this will eventually all come together. Now we have both excitatory and inhibitory signals waiting here, and they're going to be sent or summed up at the X and hillock. But what kind of signal is going to be sent? Well, what kind of signal? What kind of signal is one of them? We are going to send either an excitatory signal or an inhibitory signal. So only one message gets passed. Now, if we go back and think about this as a +1 and -1, those are going to be canceling out. So the idea here is sometimes people think when we get here that, oh, it's like 60% excitatory, 40% inhibitory. So what happens is we send across a really weak signal. A weak, yay, very weak. A weak signal gets sent saying, fire, fire. No, what happens is a signal gets sent, and that signal is sent at full force. You send either a signal at full force, excitatory, fire, or an inhibitory signal, don't fire, not something in between. Okay. It doesn't like math either. Okay. So if it's canceling each other out, the overall strength isn't going to be enough. It wants one message. It doesn't want a very complex one. Tell me to fire or not fire. What one signal am I going to send? Whichever one passes the threshold is the one that gets sent. And then that one gets sent at full strength. And only one message is going to be sent. The reason I introduce this here now is because of part of what's in this little box down here. And that is, once we start this process, it's not going to be able to fire again to send another single message down until the entire process of firing and resetting of the neuron has occurred. All right. So it can't send something down and then send another one down immediately and just keep sending them down as they start to accumulate until the entire process we're going to be talking about is completed. This neuron cannot fire a second time. So it sends a signal down, sends it at full strength, and it cannot send another signal until the entire process resetting itself back to its natural state has been completed. So we call this the all or nothing response. One clear signal is sent or no signal is sent at all. Again, in terms of the strength, I have up here to think about the idea of an elevator button. Let's say you get onto an elevator and you press the button to go to the floor that you want. And then someone else comes along and they hop on and they press the exact same button that you do. The elevator isn't thinking, oh, there's multiple people. I have to get down there quickly to get them to their floor. It just received a signal, we need you. That's the only signal it receives. That's the only signal it responds to. Doesn't matter how many times you press that button. Okay. You're not going to fool the elevator. The elevator comes because it's responding to the one signal saying, we need you to come down to this floor. Okay. Same way here with the neuron. One signal is sent. That one signal is the only message that will get sent until the neuron resets itself. Oh, Otto's back. He's a good boy. He's a Boy Scout. Huh. My voltage gate looks like a hot dog. I'm embarrassing myself. Again, this may be part of why we're not, best friends. Because he's mean. He's mean like this all the time. Looks adorable. Mean as a skunk inside. Just saying. I will say, however, in this case, he is absolutely correct. I tried so many things to try to approximate a voltage gate, but then when I tried to shrink it, it didn't work. So I ended up at the hot dog. I acknowledge it. You've already thought it along the way. I'm not embarrassed. Let's see what PowerPoint animation you've been doing recently. If so, then you can complain. Otherwise, yes, my voltage gate looks like a hot dog. Um, Fine with it. My life doesn't depend on other people saying how brilliant I am. Would be nice to hear once. However, I don't need it. So my voltage gate hot dog stands exactly as it is, and I don't give a damn what Otto thinks at this point. I'm quite proud of my voltage gate. Okay, the next part here is our axon. And the axon is this long branching extension. Now notice I have here, it's this entire section from the axon hillock, which is about here, all the way down to about here. All right, minus these bubbles, minus the myelin sheath. We'll get to those. But those are wrapped around the axon. The axon is the pink tube that's inside, going through those little bubbles. Notice a couple things on this particular graph. The first one is, let me see if I hope that's on your screen. Hopefully you can see this arrow here under the axon. Notice I have up here one pathway going from the left side to the right side. The only entry point into the neuron is through the dendrite. It goes from the dendrite only to the soma. It then goes from the soma only to the axon hillock. It goes from the axon hillock to the axon, down the axon to what eventually will be called the terminal buttons and the synaptic gap. But there is one pathway in which information travels. Starts at the dendrites, ends at the synapse. It cannot enter in any other place than a dendrite. It cannot exit any other place than at the synaptic gap that's going to do this. So the axon is a pathway from the sort of the main body of the neuron down to the next set of neurons that it's going to connect to. And there is one, notice that there's a whole bunch of dendrites, as we've covered. Again, some of the neurons have a lot more than what I've depicted here, but no matter how many dendrites you may have, every neuron only has one axon. Okay, so what that is going to mean in a practical sense before we get to what's here on the screen. Remember I said that we are going to lose neurons or parts of neurons throughout life. Again, if Junior Banquet is here, neurons are being lost left and right at the moment. However, if it is Junior Banquet and you're listening to a PowerPoint about a neuron, you have really got to start drinking because that is the worst Junior Banquet experience I have ever heard of in my entire life. Of course, I say that understanding I'm talking to people who are above the legal age of 21, because I would never, ever encourage anyone under the age of 21 to drink because it is against the law and I think against the honor code. Just so we're clear, just in case, I don't know, the president ends up listening to this one day. Just want to make sure we're okay. All right, so we have one axon, we have a whole bunch of dendrites. So let's say, for example, you are one of the non-good horse riders. So you're one of the ones that falls off a lot. Not criticizing. Horses are a lot taller than I like, so I'm not fond of them. But the idea is that I would be someone who would very likely fall off a horse. I, however, just because of my center of gravity, would land flat on my ass. You, however, at least the riders tend to land on their back and head. So you're doing it wrong. The rest of us know how gravity works. But what happens here is you take sort of a blow to the head, and let's say that you knocked off this entire set of dendrites right here. So this area right here. So both of these big chunks of dendrite has been lost. They're crushed, they break off, whatever. They're no longer there. This neuron, if that damage has been done, but that's the only damage that has been done, this neuron is still functioning. Because yes, this may be where a signal used to enter, but there are still other entry points to this neuron. All right, so as long as there's at least one entry point, this neuron can still receive a signal and then send the signal down to fire. Okay? One of the things that happens with something like a stroke is that the neural pathways, neurons themselves that are part of a pathway we use quite a bit, can get destroyed. And we see, recovery of function. I lost my ability to speak, or my ability to speak fluently or smoothly. But with a lot of practice, it comes back to a certain degree. What the practice is doing is creating a new neural pathway to get to a part of that pathway I used to have that I can now use, sort of as a detour to use the pathway which has been effective before. So if this used to be part of, think of this as an on-ramp into the neuron. If this is destroyed now, you can't do that. We now, of course, will just have to go a little bit further, connect to this one, pick it up at a road later at the next exit, or the next on-ramp, I should say, and then use that as my entry point. So again, that's really what's happening when you are learning. And knowledge is being sent and stored. Learning is really just activating these neural pathways and storing the information in our brains. The more that you study, the more that you activate those pathways, the stronger the memory trace is going to be. If you only skim something or don't study hard enough, the reason you don't know the knowledge is because your pathway wasn't strong enough. You can't retrieve it when it was necessary. So if you're doing badly on a test, let me just say up front, never blame the test. It is never the test. Okay, once in a while, it is the test. I have to be honest. Every once in a while, there's a stinker of a question that comes along. But if you did really badly on the test, it's not the instructor, it's not the test, it's that you just didn't study appropriately. Doesn't mean you didn't spend a lot of time studying, you just didn't do so appropriately. So again, if you are struggling in any class, please go to the ARC. They do have assistance for everybody who is there. Again, that's a little bit of a tangent, but it's interest psych. We want to take that kind of tangent whenever we can. Okay, so the axon, it's just one of them. So going back to finish the story, because we only have one axon, if our fall from the horse broke the axon, this neuron would now be functionally dead. Now, it may not decay, although the part that's been cut off from oxygen will. But all these dendrites, if the axon got affected, not the dendrites, the axon are still perfectly okay receiving signals. They just can't send them anywhere. The axon is the pathway through which we send it to go to the next neuron. So if the axon is destroyed, the cell is functionally non-working, non-workable as a pathway. Okay, so the axon carries a nerve impulse or the neural impulse away from the cell body down to the end, to the synaptic gap, to terminal buttons, the things we'll talk about later. And again, there is only one axon per cell, but there can be many branches down at the end here. So even though there's only one pathway, it can hook up to a whole bunch of different neurons. Although again, we'll find out not physically, but it can send information to a bunch of neurons, even if is only one pathway. Whatever that one signal is, it can be sent to a whole variety of different places. The axon itself, as you can see in this graph, and as most diagrams of axons in textbooks, is typically much longer than the rest of the neuron itself. Most of these 1 to 2 inches, although in the brain they're much smaller than that. But some of the motor neurons, the skeletal neurons, the ones traversing down to our feet and out to our extremities, those can be much longer. Some of our motor neurons can have an axon which is up to about 3 feet in length. Now, obviously, it depends on how tall you are. Being a not short person myself, I'm sure I've got some 3-foot neurons. But if you happen to sort of, chime in at a good 4'1", chances are you don't really have 3 foot to go. So yours might be smaller, but it can get up to about 3 feet. I don't know if you're like 7'10", how long it actually gets, but there's not enough of them for us to worry about. So we're just going to move on here. Okay, so now we still have those myelin sheath, those bubbles to sort of deal with. Oh, and Otto's back. I should mention that Otto, along with other of his bad qualities, he's a nudist. Well, I'll be honest, he's a nudist. He doesn't like wearing anything on his body. This picture is not Photoshopped. This is the one time, because I received a gift of a hat, and as any responsible Midwesterner, if you receive a gift, you have to use it at least one time. So I fought with Otto for about 20 minutes to cram his head into a hat, which truly was a little bit too small, popped the hat on, took a picture, sent it on to the person saying he loves it, and then we never used it again. And he also was mad at me for about 3 days because he did not like the hat thing at all. But that's actually him in his one hat that I've managed to get on. Now, Otto is saying that I should skip the myelin sheath. I would like to remind the audience, because you might remember I said that he is my sidekick, and sidekicks don't give orders. So the reality is, I'm the alpha of the house. He must be the beta then. And what that means is I'm not going to take advice from some damn dog. Thank you before. That was helpful. I'm not going to listen to you because you're a 12-pound little dog and you depend on me for your food. So I'm going to talk about whatever I want to talk about next. So nice to see you again, Mr. Carrot, but I'm going to ignore Otto. Huh. Like I said, we have gone through several Mr. Carrots along the way, and this is essentially what happens. And he apparently has done it again. In case anyone is wondering, that is Mr. Carrot number 4. That is indeed the carcass that I came home to. Stuffing across the house. The squeaker was in the bathroom for some weird reason. Don't even want to think about that. And the fronds had been chewed off. Don't know what happened to the eyes. Don't want to know what happened to those eyes, but he completely demolished it. So I'm going to take this as a threat. And as a rational human being, I'm going to let the dog win this argument because I don't need to win to prove that I'm the powerhouse of the household. I'm the mitochondria of this household. I am choosing to skip the myelin sheath for now, not because he threatened me, but because I chose to do so. So there you go. That's how it is over here at Casa del Lobo on spring break. All right, we are getting into the second part. That was just there for a break, if for nothing else. We will cover the myelin sheath a bit later, but I'm going to talk about the second portion. So that all was portion 1. Now we're moving into portion number 2, which is going to be the neuron firing. And really the neuron firing, how we typically talk about it, what we're referring to is the movement of the signal down the axon. That is the neuron firing when we talk about it. It's not the communication, which involves the entire neuron. This is the firing portion of this. Excuse me. So this is going to be sending the action potential down the axon. All right, this chart, you will learn to love it. No, you won't. But you will see it many times, and you do need to know it for the exams, and you really should know it for if you're talking about the neuron, this graph should be something you know. Other than the time down here, every other thing on this graph is something you do need to know. The voltages over here, the different steps of the process on the graph. You should be able to, if I said, talk about how the neuron fires. You should recreate this graph and then walk me through every single component of it. That's what knowing how the neuron works is. That's what it is. And even though it's the first exam in intro psych, you're going to need to know every bit of all of this for your exam. Okay, that's as strong a hint. So I hope you didn't procrastinate and wait too long to study because you got a lot of work to do to get the neuron in. Because again, there's already been a bunch of stuff. I'm just going to double down now and add a whole bunch more to it. But all of this, again, is the groundwork to understanding how the neuron works. Okay, so we build from this after intrapsych. You need all of this in place before we get there. Okay, so let's look at this. Okay, some foundational facts, things that even when I say you need to know this, people don't really take it seriously unless it's specifically on a PowerPoint slide. But this is important and you do need to know it. So I put it on a PowerPoint slide for you. The first thing is just a fact you need to keep in mind, although I'm not going to ask questions about it. But it sort of is necessary to understand how it all works. And it's a very simple idea. The neuron itself exists in a fluid-filled environment. Remember, the neuron makes up the brain. The brain exists in the skull. Inside the skull is a lot of liquid. Cerebral spinal fluid. There's blood rushing through, carrying oxygen and glucose. Everything's a bit squishy in there. So this fluid, this liquid is going to be important in terms of how this neuron actually fires. And you'll see that in just a little bit. Okay, the next thing, there are 3 specific voltages. These were all in the chart. The chart should be available, certainly, if you're a SweetBriar student, if you're in my intro class and you're watching this to prepare for our exam, this will be in the materials that chart will be in the materials that I sent with the pictures and graphs for each of the exams. If not, you can just contact your psych professor or contact me and I'll be glad to send the graph along if it helps you. Just make sure you get it to me before it's too late to help you for the exam. Okay. But people always forget these three things. These are the three things we need to actually really worry about. These are very important, but they don't seem it because we're not used to thinking this way in psychology. Biologists recognize this exactly for what it is. Psychologists, maybe not. Okay, three voltages we want to be concerned with, and the voltage is going to come from ions. Ions are simply chemicals that carry a positive or a negative charge. And it's going to be the movement of these ions in and out of the neuron that is going to change the polarity, the voltage levels of this cell when we make a comparison inside to outside. Okay, the first thing of importance is negative 70 millivolts. And this is when the neuron is at what we call the resting potential. Okay, what is a resting potential? Well, as a general biological phenomenon, biologists talk about this, and we use it in psychology slightly differently, but it is referred to as a state of equilibrium. It's normal state, it's natural state of existence. Slightly different depending on its use in psychology. For us, sometimes it just means balance, but in this case, it means this is its natural state. So the natural state is a negative 70 millivolts. It's a comparison between inside the environment of the neuron versus outside the environment of the neuron. So when it's at its resting potential, when it's at its natural state, when it's at equilibrium, there's a slightly more negative environment inside the neuron than compared to outside the neuron. How much of a difference? Negative 70. It is more negative inside than it is outside. And negative 70 is a voltage that we can measure. All right. This happens very quickly and in a very, very tiny environment. So we can't observe this. We really can't do much. However, at the cellular level, we can test out voltage. So that's why this is important, because the voltage changes document moving from one state into the next. It is through these changes in this voltage that we know what is going on with the firing process. So that's why we need to know this. Natural state, negative 70, inside slightly more negative as compared to outside. The next one is negative 55 millivolts. Okay, this is the threshold. What we're going to find out about this, it's not as important as the other two, but this threshold is we have to at least notice a stimulation. So again, sometimes someone says your name or someone says something and it's below your threshold of hearing. You didn't really hear it, so you don't respond to it. Same thing goes here. A signal is being sent. The signal isn't strong enough to kind of gather our attention. That means it hasn't surpassed the threshold. The voltage gate doesn't open. So it's just sort of like hanging out there at the axon hillock. Negative 55 is the threshold we have to be above. If we go above negative 55 millivolts, so going into the positive realm, then that is a strong enough impulse that the signal is then going to be sent further. Okay, so that's what the level we have to have at least that much change for this to continue. Then we have a positive 40 millivolts. And again, I'll tie this all back into the graph in just a bit. Positive 40 millivolts is when we reach what is known as the action potential. This is the essentially, in an oversimplified way, the expulsion of energy. This is a moment when we are going to be at our peak amount of difference between equilibrium versus change. And this is going to begin the process to start us back towards resetting. That is going to take some energy. We're going to release energy to get us back down to our normal resting state. So this, when we clock positive 40 millivolts, that means that we are ready to begin resetting the cell or moving on again into the next part. Again, to carry this through, positive 40 millivolts means that the inside of the neuron, the liquid environment inside a neuron, is slightly more positive than the outside environment of the neuron. How much more positive? Positive 40 millivolts difference. Okay, so the negative 70 and positive 40 are important because they tell us where we're at in the sequence. The negative 55 is sort of a detection sequence. We have to be above that threshold for a signal to be recognized, excuse me, to begin to activate the rest of the process. All right, so let's go back. Excuse me. And let's talk about this because I'm going to try to use this to explain this. I found that this works a little bit better graphically, so I made this animation up. It is what it is. It generally works, I think, but there are certainly a lot of them online. The ones online sometimes have a lot of extra information on them and have things that you don't necessarily need at this point. So this is a pared down version of our discussion. So not the greatest. It's my first time in animating anything, so here we go. But let's get all the components in place first. So up here at top, light blue, this is the area outside the neuron. So again, a liquid-filled environment, outside the neuron is up top. Ignore this row for just a second. This thing right here, which looks like a bunch of trees, with no leaves on them. This is a permeable membrane. Again, remember the permeable just means to open and close. So at different points, this membrane is going to open up, allow the inside liquid to come, or I'm sorry, the outside liquid to come inside, and then eventually to pump the inside liquid outside. Okay, we'll see how that works in just a bit. And then the area down below is inside the neuron. Again, also liquid filled, but this is inside the neuron. Okay, so outside, membrane that can open and close, inside the neuron. All right, notice we have a series of these, 3 sets, and they're pairs of 2. So we have a golden green one, and we have a gray and steel one. All right, now let me just, before I get into explain what each one of those are, what I need you to understand from the very beginning is we are going to learn about what happens here at this first set of gates. Okay. The process I'm going to describe, the entire graph, takes place at this portion, just at that first set of gates. As it completes the process, it creates the energy, which activates the next set of gates. Sorry to activate that little menu there if it came down in your screen. Okay. Once this finishes its process, it activates the third set. So I'm going to be talking about this process. It is one process that's going to happen multiple times. As it happens each separate time, it's going to move the impulse farther down the axon. So this is the axon. So over here are the dendrites, the cell body. Information is entering. As we move through this process, we're going to move it farther in this direction. And that's carrying the signal down the axon itself. Okay, so the energy that is created by moving these ions in and out of this membrane is going to create the energy to sort of move it further down the sequence. Okay, we have 2 pumps here. We have a sodium pump, which is the golden green, and we have a potassium pump, and they do occur in pairs. Each has a specific function, and it has some things that are important to know about them. We'll deal with each one of them separately. But notice for each set, we have a sodium pump and a potassium pump. Okay, work in concert together. When they're done, the next set of gates are going to begin to operate. Then the next set of gates after they're finished, and so on down the axon. All right, now let's populate this with all the things we're going to need to talk about the movement. And of course, this means introducing the idea of the ions. Again, we don't need to know a lot about chemicals for us to do this. You do need to know which chemicals are important. So it's going to be, you have a sodium pump and a potassium pump. Here's a hint, it's going to be sodium ions and potassium ions. So here we have the sodium ions. So Na stands for sodium. NaCl would be table salt. So sodium is sort of the salt component of that. Notice that there are really 2 things that we need to be concerned with. First is that the sodium ion is positively charged. Okay, so every single one of these ions carries with it a positive charge. All right, that's point 1. Second point, and as I'm populating this, I'm trying to make sure I can cover all the points that are important to know. The second thing is, notice that there are a lot more sodium ions outside the cellular membrane in comparison to within the membrane. So this is being carried through the normal brain. I mean, the entire brain benefits from sodium. And the idea is that this is going to be a little bit more populated with sodium ions as proportionally compared to the inside of this particular neuron. Okay, so more of them outside and positively charged. That's what we need to know about sodium ions. All right, I'm going to shrink them, shove them over to that first set of gates, and introduce the second one. Okay, so here we have the potassium ions, K for potassium. Anyone, if you're sitting there and you just have that moment where you want to take some joy in sharing your knowledge, if you thought, or as sometimes happens, you said accidentally out loud, sodium is salt, potassium is in bananas. Congratulations, you are correct. Potassium is in bananas. And whenever your potassium is low, we say, go eat a banana. Although any real scientist will tell you need to eat about 9,000 of them to have any real impact. Go to the doctor if you're dehydrated. There are other ways to get your potassium rather than eating a banana. Okay, so we have sodium ions in place all over here. Now we have these potassium ions. Again, notice two things. First, potassium ions also positively charged. Okay, so in that way, they're not different than the sodium ions. They're both going to be carrying a positive charge. One thing of difference is notice that as we're starting, there are proportionally more potassium ions inside the cellular membrane than outside the cellular membrane. I've certainly over-exaggerated it here, but there's more sodium outside, more potassium inside the cellular membrane. Okay, both of those, however, are positively charged. Okay, so let me shrink those and put those over. And let me introduce this. And we're not really going to do much about this, but for completeness sake, I just need to mention this because you're hearing a lot about it's, slightly more negative inside as compared to outside. Well, if everything we're talking about is positively charged, where's the negative at? And that is coming right here. And these are the anions. Or anions, depending on apparently where you went to or what chemistry course that you took. I learned this as anions when we do this. Okay, so these are the anions, and here are a couple things to know about this. These are negatively charged. So these carry with it a negative charge with them. They're ions as well, but they are negatively charged ions. Second thing of importance to note is that they are clustered inside, and you don't see them floating around here outside. Okay, so this is where the negative charge is going to come from, is from these anions that are down here. Third thing, we get to add one extra little fact here. Not the most important one, but again, for completeness sake, it's worth mentioning. Notice that when I shrink these, again, I'll shrink these like the other ones, these will still be larger than the rest of the ions that we've had so far. The reason that's important, the sodium-potassium pumps, they're really, there to pump out a very specific ion. One of them is a little bit leaky, so sometimes other things can leak out. The anions are a little bit larger. Again, a bit of an oversimplification. They're a little bit larger. They're not going to be the things that are going to be accidentally leaked out of the neuron. So the more negative charge will stay within as the more positive ones get pumped in and out. That negative will be there sort of a base charge to this. Okay, so let me move those over. Now notice again, I said that this is the same process done multiple times. So let me shrink this. All right, so we're going to deal with one of these. We'll deal with the entire process. I'll put the graph up in just a second. We'll go through each stage and then understand the entire process I'm about to talk about happens then at the next stage. Once it's done there, moves to the next stage, and that is carrying the signal, to fire or not fire, down the axon of this particular neuron. All right, so there's our trusty graph again. Okay, and we will walk through this as I hope as easily as possible. But again, a lot of details. I understand that. But yes, they're all necessary ones. So please make sure you understand the process. Understanding is always better than just being able to repeat it. Understanding involves deeper levels of learning. Probably you haven't hit that part of psychology yet. That comes during cognition, unfortunately. But there are ways to sort of learn this better. Certainly, in the meantime, the art can help if you need some assistance. Okay, so everything is there. Everything looks great. We are at 0.1 on our graph now. So I put this bubble up here. We are at resting potential, the natural state, the equilibrium state. In its normal state, there are slightly more negatively charged ions inside the cellular membrane than outside. The differential between inside to outside, it is negative 70 millivolts. So we're measuring this negative 70 millivolt difference between the inside and the outside. The inside more negative than the outside. That is us at rest. That is us at its natural state. Now, at this point, this neuron is okay to fire. If a strong enough signal comes along, this will start the entire process of moving it down the axon. If a signal has already started, but we haven't finished sending it, no matter how strong a signal you sent, remember, it's not going to go in. Okay? The entire process must complete. The neuron must reset. Then the next signal can be sent. Okay? So we are here before a signal has been sent. All right, here number 1. Negative 70 millivolts inside compared to outside. All right, the next thing that happens is stimulation. Stimulus is received. It can be a memory that we've activated. It can be a thought that we've had. It can be a reaction to a noise. It's loud enough to pull our attention. It can be something running across our field of vision that gathers our visual attention. The idea can be all sorts of things, but it needs to be strong enough to be noticed. And if it is strong enough to be noticed, that means it is going to surpass the threshold of negative 55. So a lot of excitatory signals would have been sent in comparison to any inhibitory, saying something's happening, go, 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 go. And that is going to be bigger than the negative 55 millivolt difference that we need to go above in order to activate the signal. So stimulation happened. We're going to say it exceeded the threshold. We're above the negative 55 millivolt difference. When that happens, notice that the first channel, the sodium channel, which is our first one, has opened up. Again, remember, this is a channel from the outside to the inside. Now, this is sodium channel. So what it's going to do, it's going to target the sodium ions. Now, again, this is the biologist. I apologize for this one in particular. This really is a little bit more complex because really only the sodium ions are going to be able to get in. It has to have the right essential shape to get through this particular chain. So the gate opens up. And it looks like just everything should rush in, but only the sodium ions are going to rush in down this channel, and they're going to go downward into the neuron itself. Because again, it's almost like opening a empty bottle underwater. Take the cap off, the pressure sort of pulls everything inside. This gate opens. There are some pumps that pull out the sodium ions into the neuron itself. Okay. So we receive stimulation, surpass the voltage gate threshold, neural impulse begins. First sodium channel open along the axon. The sodium ions begin to move in. And notice that down below, inside the neuron, it's getting more crowded, and there's less neurons in the general area outside the neuron. Now, also remember, we're pulling in a whole bunch of positive ions. These are all sodium ions, so these are all now positively charged ions that are coming inside the cell. What that means is inside the cell, which has not changed in terms of its negative charge, no new negative anions have been introduced, but we're pumping in a whole bunch of positively charged ions. So what that means is that that differential inside is now going to change. It's going to become more positive than it was before. Okay, and a lot more positive because this is a smaller space and a lot of ions are now rushing into it. So we are now leaving stimulus threshold. We've passed it. Gates have opened. The sodium ions are being passed into the neuron. We are now at stage 3. This is, in this process of pulling these sodium ions in, this is called the depolarization process. And it is the upward slant of this curve. Now notice we are starting down here at resting, surpassed our threshold. And as those ions are starting to enter, we are getting more and more positive as more and more of those ions are entering into the cellular membrane. All right. Now, at this point, we will eventually reach our next important place, which is positive 40 millivolts. So we're going to keep going until we reach that particular level. So depolarization is up until we reach that point. We reach that point. This is now point 4. And this is the action potential. When we hit this point, the apex of the curve, the sodium gate closes. So no more sodium ions can get in. And the ions that are inside the neuron are trapped inside. Okay, there is now a polarity differential. It is now slightly more positive inside the neuron than the outside environment. How much more positive? Positive 40 millivolts more positive. Okay, so the action potential, the membrane closes after the influx, which left us with an inside slightly more positive than the outside. Remember when we talked about equilibrium and the idea that this is a biological mechanism? Biological mechanisms love to reset. They love to get back to that natural state. So there is essentially a biological timer that goes off. We've met this criteria. As soon as this goes off, we are now going to begin to reset ourselves. So it's not based on time. It's based on when we reach this particular voltage change. So it's essentially a voltage gate monitor as well. When we reach that point, we're going to be sort of opening the next gate, and that's going to carry it to the next portion of this. So action potential, the energy is there. We're now going to release it, and that's going to move the energy forward going down the axon. So the gate's shut. Whatever biological deity is inside your neuron says, I want to go back to normal, and it's going to get there. So what's going to happen is the next gate is going to open. The sodium gate started us. The potassium gate is going to open next. Now we're entering into point 5, the repolarization process. And this is going downward from that positive 40 millivolts downward. Now, it goes a little bit farther than we want. We'll have to talk about that separately. But what's going to happen here is when the potassium channel opens, the potassium ions inside are going to get started to be pumped outside. Now, there is one weird little fact that we need to mention. I said this a little bit earlier, but it was just sort of out there by itself. The potassium channel is what we call a leaky filter, or has a leaky filter to it. While the sodium channel was good at just letting sodium in, the potassium certainly lets a dominance or predominance of potassium ions out, but some of the sodium ions are also going to go with it. So we're not only losing just the potassium ions, we're losing some subset of the sodium ions as well. Now, there's also more that's going on here. To sort of just, again, oversimplify because we don't need this portion, these ions get used up. We're creating and using and expending energy. These ions are going to die off, some of them. They're going to decay. They're going to be flushed out. They're going to need to, they're just used up, for lack of a better term. So not only are we actively pumping these things in and out, there's a natural death that are going to them that are inside and outside this barricade. So that's also part of the story here. That's why, again, it gets much more complex very quickly, even if we add a very small detail to it, which is why we aren't at the beginning stage. Okay, so the potassium gate open, mostly potassium is going to get pumped out, some sodium getting pumped out with it. So we're sending out what we think is a correct amount of ions, but some other ones are going to leak out at the same time. And at the same time that there's going to be some cell death inside and outside of the ions themselves. Okay, as a consequence, notice as we look at our graph, here's supposed to be our landing point. We're supposed to land here at -70, our resting point. Notice that we overshoot the mark. Now, at this point, notice that there is no specific voltage level I'm expecting you to know. This does vary. Okay, a number of factors may make it vary more or less. All right, but we're going to overshoot the mark. We let out too many of the ions, and the act of opening and closing these gates had used up other ions. Okay, so we overshot the mark here. We're a little bit too negative. okay? And now we're going to have to sort of refill ourselves up with some extra sodium, potassium ions to sort of bring the balance back up. All right. So that's stage 6 at hyperpolarization. At some point, that potassium gate closed. We now have more than wanted negative charge inside compared to outside. So we're still not at resting. Okay, we went too far. We got to get back to that resting point. So we're going to have to now repopulate. And that's what's happening during hyperpolarization. While resetting, the neuron actually overcorrected, some leakage, some decay. It dropped below that resting state, which is where we're supposed to end. And now we have to repopulate by generating more sodium and potassium ions. We're pulling them, again, from the bloodstream and from other sources as well. The mitochondria is living up to its powerhouse name at this particular moment. Eventually, we will repopulate, and we will have reached back to our resting state of 0.1. Now, how this works, though, in practicality is when we expend the energy to do this, going down this repolarization, yeah, we do overshoot it, but we did produce a bunch of energy. And as a consequence, while this portion of the curve is starting to repopulate, the next set of sodium potassium pumps are starting their depolarization process. The energy created from this is going to activate the next set in the chain. Okay, so these two things are going to happen at once. This portion of the neuron is going to be repopulating. The depolarization of the next set of sodium potassium pumps is going to start kicking off. And again, that's just going to continue all the way down until it reaches the end of the neuron. Okay, now that process happened here, and then it happens all together. So here is essentially what it looks like. I'll let it run a few times. Notice that as they're going down, the bottom is getting filled up with more of the sodium ion. As the potassium gate opens, it's getting filled up with more potassium, and they're being redistributed, repopulated as we go along. But first set of gates, sodium in, potassium out. The next gate, sodium in, potassium out. Signals move further. Next set of sodium gate, letting ions in and pumping out the potassium. So that is going to go on all the way down the axon. The exact same process, all of those stages we just talked about with all of those voltage markers is going to happen over and over again. And that is what's going to transport the signal down the axon. Okay. Now, back to the myelin sheath, because it's a little bit safer to do so, and this really is only partly related to the firing sequence. And remember that there's a whole bunch more neurons actually are unmyelinated than are myelinated. So again, this isn't something that is going to be found in every neuron. It's in a very, very small percentage of them. Okay, so what is the myelin sheath? Well, in the diagram here, this is those bubbly things around the axon. And they really are, it's fat and protein cells. But it's going to form a membrane around them. And notice there's a little gap in here. You don't need to worry about that. That's something known as a node of Ranvier. But just understand that this whole set here is called the myelin sheath. But they are not, it's not just one sheet, it's these individual bubbles that are there. Okay, now people really don't necessarily get the story unless I sort of add this fact. What is sort of fat and protein shells shell-like? If you've ever worked with, this is kind of gross, but if you've ever worked with raw chicken and you've pulled the skin off, that sort of weird gelatin goo that's in there and those little white pockets that are stuffed in the corner of the chicken, those white pockets are fat and that gooey stuff is protein. So that's really what is around this myelinization. So congratulations, we're essentially the better part of our brain is like a chicken cutlet. So there you go. But it wraps around the axon. So it's no place else but on the axon of only a select group of neurons. When this is wrapped around, it's going to actually create what's known as white matter. So if you ever heard about the brain, there's gray matter and white matter. White matter are things that have the myelin sheath. Gray matter is everything that doesn't have the myelin sheath. Okay. Now, what is this and why is this important? because again, I could have left this off, but I didn't for a very obvious reason. And it is because that this really does help the neuron function if the neuron does have this with it. So there are three functions that this myelin sheath is going to do. The first thing is, and I think the best way to think about this is a coating of insulation. Okay, so it's going to wrap around, protect the wire, which is what the axon is. Something sending a signal, an electrical signal down. It's like a wire. And this is insulation around it. So this is going to not necessarily ground it, but keep it from sort of leaping out. All right, so three functions. The first thing it does, it acts as protective insulation. So the axon is a little bit more resistant to damage if it's going to be there. Not a lot. I mean, it's a little bit of fat. It's not going to help you all that much, but it helps enough in some cases. But because it's insulation, what it's going to do is it's not going to get as much of a chance of it to arc out. Remember, if this was an unexposed wire, hopefully you've learned in life, probably the painful way, not to touch an exposed wire, because if you touch an exposed wire, the electrical shock just goes right into you. Having this protective coating around it stops that from happening. This is, again, insulation, the coating over the wire itself. This is going to protect the signal from sort of jumping out. So we know that this is at least one thing that can happen. The disease multiple sclerosis is a disorder where the disease itself is going to actually attack the myelin sheath more than other areas of the brain. It's something where this is targeted by the disease itself. And what happens in multiple sclerosis is when a signal is being sent, instead of staying within the pathway, so I'll try to put my cursor back up again, instead of staying in the pathway it's supposed to, let's say this third bubble has been taken out. As it's traveling, sometimes it may get to this point and just jump. And it jumps and it activates another neuron. It just activates another sort of dendrite. Instead of doing it the normal way, and being a chemical messenger, an electrical arc is going to shoot out. And what that's going to do is potentially destroy the dendrite or whatever part of the neuron or neural material that it is touching. So this is one of the reasons why we see those Parkinson's-like symptoms sometimes, the shaking, the jitteriness, is because we don't really have that pathway where it's being kept within the normal pathway. Second thing, we don't normally think about this with insulation, but if you have something insulated, the electrical signal or the impulse itself, because it can't go anywhere except down this pathway, it's going to move faster down that pathway. It's sort of like squeezing it a little bit, and the pathway is going to be broached quicker. So it's going to travel down the entire length of the axon faster. So these myelinated axons, these myelinated neurons, actually fire faster, quicker. They finish and reset quicker than neurons that are not myelinated, okay? And more efficiently because it can't arc out as well. Lastly, it's going to maintain the strength of the impulse. This one we don't need to worry too much about, although I have a graphic that will show this. It's a little bit too much for us to worry about the propensity of the neural impulse going down. We just, at this point, it's going down. It's going down to the end of the neuron. But if it doesn't have this myelin sheath around it, sometimes the impulse weakens as it goes down. All right. So here is the difference. Now, there's really two things you can notice. The first one, obviously, is the myelinated axon. The one down at the bottom is not. Certainly notice that the impulse, that blue sphere, moves along quickly, much more quickly than the one down at the bottom. So that's most of what I talked about. The fact that, as you notice in the second one, it's getting smaller and vanishing, that's that third point. We're not going to worry about that, but it's on the video here, so I might as well talk about it. But we really want to care more about the fact that it moves faster. It's more efficient moving down there because it doesn't arc out of that. Okay, now I put this in here because we're about to change to the next portion. Truthfully, the first time I had this in lecture, this was just my where I stopped updating the lecture, and I just forgot to take it out. However, the students liked it. It sort of cleared the mind for just a second. So it seemed worth it for me to identify where I'm hitting the different sections of this. I must say that is not my dog. My dog, even though he's a bit of a bully, is not one of these googly-eyed Boston Terriers. And that may be something you like. I don't. It kind of freaks me out when their eyeballs go in different directions. Sorry, that's just what it is. However, I can say that even though that is not my dog has done every single one of those poses multiple times. And this one down here, if my cursor isn't working, it's the bottom right one. That is right before he starts spinning around in circles and moving towards the door. Don't know what happens, but he just spins like a top. And then he'll stop and grab my pant leg or something, which is why all of the stuff I wear on the house is frayed at the bottom, because Otto just spins, and when he gets dizzy, he grabs on for dear life and rips my pants. So there you go. You wonder what a professor's life is like? That sums it up perfectly. That's how exciting our lives are back at home. Okay, but again, my dog being better looking than this one, obviously. Yeah, look at this one. Kind of tell, right? A little stupid. Yeah, whatever. Okay, mine may be a bully, but he's an attractive bully, so he's got that going for him. And his eyes focus, which I appreciate. Okay, let's move into the last part of this. I just have the feeling I'm going to get emails from people with who like googly eyes and dogs, and they're going to yell at me. Whatever. So the last part, finally nearing the end. This portion will go a lot quicker than the other two. Don't worry, we really are getting close to the end. Here we're going to talk about transmission between the neurons, how we communicate one neuron to the next. It's gone down the axon. Now we just got to finish the journey and get across to the next neuron. Okay. One thing I will mention is that notice that, so like this image that's up on the screen right now, there are a ton of these beautiful images that are out there that show neurons communicating between the end of one and the beginning of another. There is no picture that is big enough for me to cannibalize or has the right components to it, so I had to go a little bit more low-key in my graphics. So I'm just saying out there, people with skills who work in neuroscience and graphics, make some better graphics for me to poach. It would make my life a little bit easier. All right, just saying. So lower your limit or lower your expectations. This looks cool. What's going to happen next? Not so much. All right, first off, just from your textbook or from a textbook, I can't say which class you're in. So here's everything we've covered. Those are the dendrites up at that one end of the cell. This is the soma, the nucleus. Here's the axon bending down, and it's this portion, the end. So these would be all the things coming out the very bottom or at the very right of our typical neuron. This is the part we're going to be dealing with right now. There are some special components, so I do need to sort of identify them, and then we'll talk how this all works. And the end portion, at least for now, is going to be relatively simple. All right, the first thing we have is something called a terminal button, or the axon terminal, if you prefer. They're used interchangeably. I haven't found any rhyme or reason to it, so both of them are perfectly fine. It's this area right here. It's like that bulb that's down at the bottom, and inside that bulb are going to be these, what we're going to learn, these are called vesicles, and inside those vesicles are going to be our neurotransmitters. So these are going to be where the chemical messengers are being stored. So this is really a storage unit at the end of every neuron, and stored within that are going to be these groupings of neurotransmitters in these specific little vesicles, little cups that are there to hold the neurotransmitters until they are needed. So the action potential has reached the end of the axon. A storehouse of chemical messengers. Sorry about that. Sometimes I leap into professor speak. It's like the powerhouse of the cell. The chemical messengers and neurotransmitters are here. They're going to be used to carry the signal to the next neuron. So what is a neurotransmitter? Again, we can keep it relatively simple for now. The neurotransmitters are simply chemical messengers that carry the message across what we'll call the synaptic gap, the space between them. Notice in this diagram here, cursor back, here is the end of a neuron. This is a terminal button of one. Here's the dendrite of the next neuron. And notice this white area in between. That is actually a physical gap. Okay, so remember, this is a fluid-filled environment. So when the neurotransmitters are released, they're going to float out over this gap and embed themselves in the next neuron. Okay, that is what carries the signal to the next neuron. These neurotransmitters carrying across this fluid-filled gap. The reason we save talking more about this to something like abnormal is because really this is where medication comes into play, speeding up or slowing down this process by changing what's happening at the synapse. So again, we're going to shortcut it here. It'll be picked up on in later classes. But the neurotransmitters are the chemical messengers, and there are over 60 separate neurotransmitters that are available. In psychology, you can probably say there's about, at the undergraduate level, probably 10 that you'll hear about an awful lot. But today we're just going to focus on the main ones. And I went through and picked, and I think everyone would agree in the field, these are the 4 main neurotransmitters that you're going to run across in the intersect classes or the lower level classes in psychology. Okay, so these are all neurotransmitters, but they do different things. So the first one is dopamine. So in this, I'm sorry, let me explain this chart here. Dopamine is, or this first column is the neurotransmitter itself. The second is the kind of role it plays. And the third column is the place you're most likely to run into this for the first time. All right, so I'm just sort of, I just sort of geared out where you're most likely to hear about it other than in today's lecture. So these are the ones that I went with because these are the ones you're going to hear about first. And again, most, and there are reasons why we hit these first because they are going to show up a lot for us. So dopamine, its main role is activating the things involved in reward and motivated behavior. So this is going to play a big role. Anyone, and by the way, anyone who's in developmental psychopathology, we have just spent a long time learning about the dopamine pathway and the reward circuit of the brain. And that's really where dopamine comes into play, although it's really an all-around hitter. This one does a lot of stuff in the brain. So this is without question the one you're going to run across most. But this reward-motivated behavior, this is a place that you're going to run across it in detail, but that may be in the later stages of the curriculum. So this stimulates the emotional desires for a reward in the form of pleasure. So when we engage in an act, dopamine is released. Dopamine acts as something that provides a pleasure to us. It might be a physical, might be an emotional, might be a mental pleasure to us. But the idea is it causes us to feel better as a consequence to increase that particular behavior from showing up again in the future. This can be both quick acting or slow acting. And something like addiction or gambling, dopamine is going to be the main transmitter that's going to be at play in the addiction cycle. However, that's not really the place you're going to hit first. Most likely in interpsych, we don't really talk about addiction at this level, just in passing, if anything. We're going to run across it first in interpsych is going to be with schizophrenia. And it plays a very, very important role there. The lack of dopamine is found in individuals who have active cases of schizophrenia. I'm not going to go further than that. You don't know what schizophrenia is yet. And we're not really talking about the brain. I'm just giving you an overview of where you're going to run into this stuff. But dopamine, tied into reward behavior, tied into addiction, important in dopamine. It's low levels of dopamine in schizophrenia. The second neurotransmitter is norepinephrine. Now, if we are on the other side of the pond, Europe still tends to refer to this as noradrenaline. So these are the adrenaline substances. We just call it norepinephrine over here. So this is going to be the brain chemical that gets released when we need to mobilize the brain and body for action. It increases our mental alertness, our mental focus, helps us retrieve things from memory, knowledge about, is this thing coming towards me dangerous or not? Okay. Is it a threat or not? So threat assessment would be part of this. And obviously, I mean, we kind of know where adrenaline is going to show up. So you're going to run across this probably most frequently when we talk about fight or flight responses. Again, although it does show up with other things, like mania, hyperactivity, it will show up. But the fight or flight response is something you'll run across in intropsych. So that may be the first place that you run across this there. But this is going to be the getting our mind ready and getting our body ready to take action, fight or flee, as the case may be. The next one, very common one. People know a lot about this one, so it makes the list just for that. Serotonin is their third neurotransmitter. Serotonin helps regulate our mood. So this will be in medications for both antidepressants and anti-anxiety drugs. When our serotonin levels are off, our anxiety or depression can increase or decrease. It's in play with social behavior. So when we socialize with somebody else, our serotonin levels increase. When we're hungry, when we're sleeping, memory duties, it's involved with sexual desire and sexual functioning. Again, wears a lot of hats in this one. But again, the place we're most likely to hear about it first is when we're talking about mental illness and most likely with depression. Serotonin and a class of drugs known as serotonin reuptake inhibitors are a common treatment for things like depression and anxiety. So you will have heard about it likely from that. And then we have GABA, and I put this one, there might be some that are more common than this, but GABA makes a list because everything else seems to be more excitatory than inhibitory. GABA is the most important inhibitory neurotransmitter. So this is a neurotransmitter that's going to get released when we need to calm down. It's going to calm down the central nervous system, calm down our mind racing, calm down excitability at the neuronal level. Again, excuse me. Again, this one mostly coming up in relation to mood disorders like anxiety. So medications, there's GABA-based medications as well. Okay, the synaptic vesicles, really not much to that. These are just the holding places for the neurotransmitters, and they're found in the terminal button. Ta-da! I mean, that's sort of it. That's sort of anticlimactic, but there it is. The synapse, though, we know sort of a lot about. Remember that this is the gap between the end of one neuron and the beginning of the next. This one I find a lot of variation what people call it, but the synapse, the phrase synapse should always be part of it. It may be referred to just as a synapse. Some people refer to it as a synaptic cleft. Cleft just means gap, or the synapse gap. So all of those mean the exact same thing. And what does that mean? So it's that space between the neuron, the space between the end of a neuron, the terminal button, and the beginning of the next neuron, the dendrite. The space between them, they're separated by obviously a very tiny distance, but that distance is there because if not, remember that this has been electrical signal so far. If they were physically touching, the electrical signal would just continue on. We need that physical separation in order to make sure that the signal stops. We switch gears and go from electrical to chemical to finish the signal. Okay, the release neurotransmitters get the signal to release, and the excitatory or inhibitory signal may release a different kind of neurotransmitter. All right, so whatever a signal is given, a set of neurotransmitters is released, and they're going to float out into that gap, embed themselves on what we're going to call the receptor site of the next neuron. Receptor site is nothing fancy. It's a place on the dendrite where the signal gets picked up. Okay. While in those receptors, excitatory or inhibitory actions occur in the receiving neuron, it receives the signal, keep firing, stop firing, and it sends that again, to either keep the cycle going or to stop the cycle if it hasn't done so far. And lastly, again, not so much for us here, just as, again, for completion's sake, medications or drugs can extend or limit the amount of time that the neurotransmitter is available within the synapse in order to activate the next neuron. So we can sort of pull it back in really quickly, or we can just leave it out there. If we leave it out there for a long period of time, that would be like a depressant. Because my neurons are not firing quickly, I feel slow, I feel sluggish, I feel clumsy. If things are firing too quickly, excitatory, and sort of pulled up really quickly so it can refire again, it's going to be like a manic thought. Your mind is racing, that sort of thing, jittery from nervousness, or just jittery from what we think of as adrenaline. Those things would be the outcome here in terms of what the drugs would do. Okay, so here is my cheap version that I could sort of do. So communication between the neurons. This lightning bolt, really the only cool part of this, is a neural impulse coming down in its electrical form, and it has now reached the terminal button. which is this portion right down here. These are the synaptic vesicles, which are holding the neurotransmitters. All right. So the neural impulse has traveled down the axon. It has reached the terminal button. Okay, step one. Oh, down here, these are those receptor sites. So this is the next neuron here. Okay, so one, the signal has reached the terminal button. Step two, stuff happens. You don't really need to worry about everything that happens next. This is actually weirdly complex. We're going to save the intricacy of this until later. So it reaches it, stuff happens. Okay. However, I can pick up after that stuff has happened. All right, number three, the synaptic vesicles that are in place open up. So these two vesicles open, and the neurotransmitters that are inside begin to flow out over that synaptic gap or over that synaptic cleft. It releases the neurotransmitters into that gap. They float across, and at this point, since they haven't embedded themselves in this place that's there to hold them, we're going to see that we haven't received the signal yet. So they're just being floated out right now. Now, when they do hit, when they embed themselves in the receptive juncture of the next neuron, so at the dendrite of the next neuron, they activate. This site activates, and again, either an excitatory signal or an inhibitory signal will then be passed further down into that particular cell. Now, not going into great detail on this, but the right kind of neurotransmitter is sometimes necessary to activate the next neuron. So there's something known as a key lock system. The right key has to be inserted into the right lock. So if I want to stop a signal, let's say that all of these are set to activate when it receives dopamine. If I receive an inhibitory signal, one thing that I can do is release a lot of things that aren't dopamine, but can still fit into this. Because they don't activate, these receptor points don't activate until the right key is into the lock, sometimes a neurotransmitter can just block another neurotransmitter, the correct one possibly, from taking action. And that's one way in which this can stop an impulse that's going to be there. Okay. If the right key is hit, then the signal is being sent. Again, either one to keep going or one to stop. Remember, we need enough of the inhibitory signals to stop the neuron from firing. This is one neuron sending one signal. Remember, they're going to get summed up, and they would then stop if that inhibitory signal in the next neuron is stronger at that voltage gate that we have. All right, the last portion. We then go through a process known as reuptake. This is, again, another biological mechanism. Reuptake means to take back up. And the re is just there, I guess. But the idea is those neurotransmitters, some of them get used up, some of them get flushed out, but there's still some neurotransmitters floating around out there. And again, until we're finished, the neuron can't fire again. So part of it's getting ready to reset itself. It's going to have to suck back up all of those neurotransmitters that are still left outside, pulls them all back up into the vesicles again, close up, and then another signal is sent saying that done here. Okay, so the neurotransmitter sucked up into the vesicles close up. The message is then set back up, or a different kind of message. We're not even going to bother with that one today, saying the neuron is now ready to fire again. Once that signal is reached back at that axon hillock and at that voltage gate, then the neuron is ready to fire again. And this process is just going to continue on and on. Oh, goodness. Thank God we are done. That is the entire neuron. That is a lot. I understand that. And there you go. That's everything you need to know about the neuron. Certainly, I'll just leave it up here so students can go back and watch whatever portion they need to watch. Again, if you're currently in classes, whether you're a first year, a senior, or anyone who just has weird interest, you can always stop by and talk to any of us during office hours, and we will be glad to talk about the neuron with you. It has never happened in my lifetime, but apparently if you say those sorts of things, you can apparently will it into action. So we will see if anyone has any damn neuron questions as we go forward. All right, thank you. I hope that was helpful. I hope you got some use out of it. And I agree, that was a lot of information. Welcome to psychology.